I think now is live. Yeah. Okay. Oh, yeah. Is it live or not? Pak Sabah, Rafif, can you check? This one. Oh, belum ada tulisannya live ya?
It is live, sir, on YouTube.
Sudah
Oh.
live, Pak.
I just
Izin.
Oh, okay, good.
Sudah live.
Sudah live ya? Just a moment. Let me see. Okay. Now, yeah. So, hello everyone. I am Edi Tribaskoro. Good afternoon to all of you, and welcome again to the Combinatoric Today series. It's our great pleasure to see you again in this program, Combinatoric Today series, and I would like to announce that this year we will have 6 edition altogether until this December, and today we come to the 4th edition for this year. And in this occasion, allow me to thanks to the Dean of the Faculty of Mathematics and Natural Sciences for his continuous support and encouragement in conducting this event. I am privately very happy that through this series, we could invite prominent combinatories from all over the world to present the current and update development of our fields with combinatoric and graph theory. And today we are delighted to have Professor Hajime Tanaka as a speaker. Professor Hajime Tanaka currently serves a full professor at the Graduate School of Information Sciences, Tohoku University, Japan. And Professor Tanaka has developed a notable research profile with a particular focus on algebraic combinatorics, graph theory, and their applications in various domains. And today, Pak Hajime will give lectures on linear semi-definite programming techniques in combinatorics, and will be chaired by Dr. Suhadi Widosaputro. Okay, and I should mention here that this program is brought by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, with a collaboration with the Center for Research Collaborations on Graph Theory and Combinatorics, Indonesia. Now I let Dr. Swati to chair this lecture.
Okay, thank you very much, Professor Aditri Baskoro. So, can you hear me?
Yeah.
Yes, okay. Okay. So Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, and good evening for all participants of the 4th Combinatorics Today series in 2024 from various time zones. My name is Suhadi Widosaputro. So today I am the moderator for this Combinatorics Today series. I am very pleased to see you here and welcome of all participants to this seminar. The theme of today's series is about linear semi-definite programming techniques in combinatoric. Okay, the talk, I'm sorry, I will share slide first. The talk will be given by Professor Hajime Tanaka. He is a great combinatorist and also algebraist from Tohoku University. He received master and also doctoral degree from Kyushu University under supervision of Professor Eiichi Banai. He started his career as a research fellow in 2001 until 2004 at Kyushu University, and then in 2004 until 2007 at Tohoku University, Japan. He also visited some universities in South Korea and also in US for continuing his research. One of them was a honorary fellow at University of Wisconsin-Madison, USA, hosting by Professor Paul Terwilliger in 2010 and 2011. In 2007, he became an assistant professor at Tohoku University and then continue become associate professor in 2012, and now he is a fully professor in the same university since April 2024. He has published 38 papers in number of top-level international journals, including linear algebra and its applications, Ars Matematica Contemporanea, Quantum Information Processing, the Electronic Journal of Combinatorics, Symmetry, Integrability, and Geometry, Methods and Applications, Graf and Combinatorics, Kombinatorika, and Bulletin of the London Mathematical Society. He has been also invited to present his talk in many international events. Professor Hajime Tanaka is also member of Mathematical Society of Japan and the Institute of Combinatorics and its Applications. He is also a referee in many mathematical and combinatorial journals, including Discrete Mathematics, Annals of Combinatorics, Journal of Graph Theory, and SIAM, Journal of Discrete Mathematics. So now allow me to welcome the speaker, Professor Hajime Tanaka, to deliver his presentations. The audience who want to ask a questions can ask directly in the discussion session after Professor give his talk, or maybe you can write your questions on the chat box. So, Professor Tanaka, the time is yours. So you have 60
Udah
minutes
foto dulu Pak
to
Sunadi.
60 minutes?
Foto
60
dulu.
minutes.
Yeah,
So, but
thank you very
first,
much.
so Professor ready? So before you give a talk, so first we have photo sessions.
Oh, photo session. Okay.
Okay, photo session. Yeah,
Photo session first.
great.
This is
Okay,
the
so
very
please,
important
yeah.
sessions.
Please open your camera, everybody. Yeah. So we have a photo session, group photo. Yes, many people, nice faces, and okay. Yeah. Just a moment. I'll also open my second camera. Okay, 1, 2, 3. One more. Other slide. 1, 2, 3. Okay, that's all. Thank you. Now back to Pak Suwadi. Yeah.
Okay, thank you, Professor Ediba Baskoro. So, Professor Hajime Tanaka, so you have 60 minutes to deliver your talk.
Mhm. Okay, then first, let me share my screen. So can you see
Yes,
the
perfect.
slides? Okay.
Yeah.
So first of all, thank you, Suhadi, for the very detailed introduction. Okay, let me begin my talk. The title is here, Linear and Semi-Definite Programming Techniques in Combinatorics. And here is a very brief, not an introduction, but as you know, I specialize in algebraic and spectral graph theory and also algebraic combinatorics. And I have visited Bandung several times. And the first one was in 2012. And in 2015, I gave a series of lectures. So this is the first one. I'm wearing a batik. This is batik.
Yes.
This is the last one, but this is not the batik. Okay, so now I think that the title of my talk was a bit too ambitious. So actually, the topic in this talk will be very limited to the following problem. So the objective is as follows. So we want to use a linear LP or semi-definite SDP programming to bound the independence number of a graph. So this is our objective. So it's very much limited. So actually, SDP is used everywhere in combinatorial optimization. So our objective is rather limited. Okay. So the independence number of a graph is as follows. So here we take a finite simple graph. So because it is simple, so there is no loop or multiple edges. Okay. It is a finite simple graph, and the independence number alpha of G is defined in this way. So this is a maximum size of an independent set. So here, U is a subset of the vertex set. It is called independent if there is no adjacency. Okay, so such a set is also called stable set or co-clique. Okay, so let's consider this kind of simple example. C6 fixed cycle. In this case, for example, we can take these two vertices. So they are non-adjacent. So they form an independent set. But obviously, this is not maximum in terms of the size. Actually, we can take three vertices in this way. Okay? And this is a maximum independent set. So there is no independent set of size 4. So the independence number is 3. Okay? So it's an easy concept. But it has many applications. So in fact, many problems in combinatorics or discrete mathematics can be interpreted as finding or bounding the independence number of a graph. So for example, in coding theory, in this case, the vertex set is a set of binary words of length n in this way. And let us take two binary words. Then their Hamming distance is defined in this way. So this is a number of indices where x and y differ. So this is called the Hamming distance. Then in coding theory, I should say in classical coding theory, we are interested in finding or bounding the independence number of this graph where, so here delta is fixed, but x and y are adjacent whenever their Hamming distance is less than delta. Okay, because x and y are distinct, so it should be greater than 0 and less than delta. So what does this mean? So this, if we take an independent set in this graph, then because they are not adjacent in an independent set, so x and y are not adjacent, then this means that their Hamming distance is at least delta, because they are not adjacent. Okay. So this means that this independence number is nothing but the maximum size of codes or vertex subsets with minimum distance at least delta. So this is the meaning of the independence number in this case, in this graph, okay? So suppose that this is the vertex set V, and suppose that they are independent in this graph, then this means that any two vertices have distance at least delta, okay? So in this case, we can write this kind of balls. So these balls have radius this size. If we write this kind of balls, then because they have distance at least delta, so these balls do not intersect with each other, okay? So this means that this code or independent set can correct at most this number of errors because they do not intersect. So if this kind of error occurs during communication, then we can detect the original vertex. So this code or independent set can correct this number of errors. So this is a mean encoding theory. So in this way, very classical problem in coding theory can be translated into a problem of bounding or finding the independence number of a graph. Okay, so it has many applications. And as I mentioned today, the title of my talk is very ambitious, and we are only interested in independence numbers, but there are many use of linear and semi-definite programming. As I mentioned, it is used everywhere in combinatorial optimization. So here are some latest papers. So for example, in this paper, Wagner used LP to refuting several conjectures. And maybe some of you are experts on Ramsey theory, so you might be interested in this paper. So they used SDP to determine several Ramsey numbers. Frankly speaking, I have not read this paper yet. So it looks very difficult for me. So, but maybe some of you are very interested in this paper. So if maybe we can read this paper together. So, but it looks very difficult for me. Anyway, let me begin with the basics about positive semi-definite matrices. So because I guess there are many graduate students in the audience. So let B be a real symmetric matrix of size n, then it is called positive semi-definite if this quadratic form is non-negative. So for all u, this is a column vector. So if you compute this matrix, this is a 1-by-1 matrix, then you get this one. So this is a quadratic form. So this is the definition of positive semi-definiteness of a matrix P. Now, there is an equivalent condition. So let us take the eigenvalues of B, lambda 1, lambda 2, lambda n, then B is positive semi-definite if and only if all of these eigenvalues are non-negative. So these are equivalent conditions. So let me show you one simple example. So let us consider this 2-by-2 matrix. If we compute the quadratic form, so just apply this formula, then you get this one, because all entries are 1, okay? But then this is u1 plus u2 squared. So it is obviously non-negative. And also it is very easy to compute the eigenvalues. So this is an eigenvector with eigenvalue 2, and this is an eigenvector with eigenvalue 0. So there are two eigenvalues, 2 and 0. These are non-negative. Okay. So it's a very simple example. Now, here is one important property about positive semi-definite matrices. So let us take two matrices, real matrices of the same size. Then let us define their inner product, BC inner product. So this is defined by this one, B transpose times C, the trace of this matrix. So actually this is the sum of all Bij,Cij's. Okay? So this is literally the inner product of these two matrices. Then one important fact about positive semi-definite matrices is that if both B and C are positive semi-definite, then their inner product is non-negative. So if we view these matrices as n squared dimensional vectors, then they form acute angles. Okay? So now let us discuss the very famous and important bound on the independence number of a graph. It's called Lovász theta function bound in 1979. So let us take a graph with n vertices. So this is a set of all real symmetric matrices. And here, the rows and columns of these matrices are indexed by the vertices. So let J be the all ones matrix. So this is a matrix, all of whose entries are 1. Then this is the Lovász theta function band. So the definition is a bit complicated, but it is the solution of this maximization problem. So here, in this maximization problem, we want to maximize this inner product. So, but what is this inner product? J is the all ones matrix. So this inner product is nothing but the sum of all entries of X. Okay, this is the sum of all entries of X. So we want to maximize this one under various conditions. Number 1, this X is positive semidefinite. Number 2, Xi inner product. Now, what is this inner product? So I is the identity matrix. So this is the sum of the diagonal entries of X. So this is just a trace of X. So this is a trace of X, and this is the sum of all entries of X. Okay, so this X must have a trace 1. And here are 2 other conditions. Number 3, if X and Y are adjacent, then the corresponding entry must be 0. And finally, all the other entries must be non-negative. By the way, this condition was not included in Lovász' original paper, but this is just because his motivation was different or more difficult. So he was interested in the so-called Shannon capacity of a graph. But if we restrict our attention to the independence number, then this condition makes sense. So this was added later by Shriver in 1979. So the same year, but the same year and the same journal, but this paper appeared later than this one. So this is an example of a semi-definite programming problem. So it is complicated. But here is the theorem. So this theta function gives an upper bound on the independence number of G. Why is it? In the next slide, I will show you some example, easy example. So, but the rough idea is that from each independent set, we can construct a specific matrix X satisfying all of these conditions. Okay, and then in this case, this inner product, the sum of all the entries, corresponds to the size of the independence number. Independent set. So, but this is a maximization problem. So, because this is a maximum value, so obviously this theta G must be an upper bound of the size of independent sets. Okay. And this is how we construct such a matrix X. So let us take U to be the characteristic vector of U. So this is the column characteristic vector. So it is a 0, 1 vector. And then we take, we denote it by XU, but we take this kind of matrix. So U is a column vector, and U transpose is a row vector. So it is a square matrix. Okay, n by n square matrix. But this is essentially a one-dimensional projection, rank 1 projection. So obviously this is positive semi-definite. But in the next slide, I will show an easy example. Okay, these are the constraints, and this is our construction. So let us consider this C5. Let us take these 2 vertices. So then 1 and 3 are independent. Okay. So now this is the characteristic vector. So it has 1 in position 1 and position 3. Okay, then this is the transpose. And we divide it by the size of U, which is 2. So it is 2. Then this is a resulting matrix. Okay. Then let us first consider this one, X inner product J. So this is the sum of all entries. What is the sum of all entries? So here there are 4 ones. So 1, 1, 1, 1. So 4 divided by 2. So it is 2. So 2 is the size of U. Okay. And it is positive semi-definite, as I mentioned before. And what is the trace of X? The trace of X is, as you see, 1 plus 1, 2, divided by 2. It is 1, right? So this condition is met. And then what about the third condition? So if X and Y are adjacent, so suppose, for example, let us take 1, 2. 1 and 2 are adjacent. Then what about the 1, 2 entry? This is 0. So this condition comes from the fact that it is an independent set. Okay? So 1, 2 entry is 0. And what about 2, 3 entry? 2, 3 entry is 0, and so on. So this condition is met. Finally, this matrix is obviously non-negative. All entries are non-negative. So this condition is also met. So in this way, we can construct a specific matrix from each independent set. And this is a maximization problem. So this must be an upper bound on the independence number of G. But in fact, in this case, so this maximum value is square root of 5. So, and obviously this independence number is 2. So there is a gap here. So this value is larger than the actual independence number. But the square root of 5 is in between 2 and 3. So although this is bigger than 2, but we can round. Because independence number is obviously an integer, so we can round it. So if we round square root of 5, then we get 2. So in this sense, this bound is tight, but the actual value is not tight. And in this paper, Lovász gave several equivalent formulations of this theta function. One of them uses the duality. So this is our key tool. So the dual problem, SDP problem, is like this. So again, this looks a bit complicated, but this is a minimization problem. And we want to minimize y. So y is a scalar. And z, and we take another variable, matrix variable z. And the conditions are as follows. Number 1, y times identity minus j minus z. So it's a bit complicated. So this strange matrix is positive semi-definite. This is number 1. And number 2, whenever x and y are non-adjacent, including the diagonal entries, the xy entry must be non-negative. So if we impose these two conditions, then the main theorem, so actually this is a basic fact about positive semi-definite programming. But this original problem and this dual problem, they are equal. So here I want to show you the so-called weak duality. So I will show you this is less than or equal to this one. So I will show you this direction. So let x and y, z be feasible solutions. So this x satisfies all of these conditions, and y, z satisfies this condition. Let us take feasible solutions, and let us consider this one, y minus xj inner product. Then, so first we use this condition. Then as you see here, this one, because of this condition, this one is equal to y, okay? Okay, because of this condition. So that's why we have equality here. Next, we use this condition. So first, let us write this matrix as S. Okay? Then this is S plus V, right? So this is S plus C. So S is this one. So that's why we have this equality here. This is S plus C, so it is XS plus XC, right? So we have used this condition. And then now let us use this condition and this condition. Then X and S are both positive semi-definite. Then, as I mentioned before, if we take the inner product of two positive semi-definite matrices, then this must be non-negative. So this is non-negative because of this and this. So this is non-negative. Okay. Finally, we will use these conditions. So now let us compute XC inner product. So this is a sum of X, XY, Z, XY. So if X and Y are adjacent, then XY entry is 0, okay? So this is 0. So if X and Y are adjacent, then this is 0. On the other hand, if X and Y are non-adjacent, then this is non-negative, and this is non-negative, so this is non-negative. So in either case, this term is non-negative. So this is non-negative. So as a result, this is non-negative. So in this proof, we use all of these conditions. Okay? So Y minus Xj inner product is non-negative. So in other words, Xj inner product is less than or equal to Y. So this is true for any pair of feasible solutions. And this is a maximization problem, and this is a minimization problem, but this is true for any pairs of feasible solutions. So it should be true for their optimal values. So theta of G must be less than or equal to theta star of G. So this is the proof of this direction. So the other direction is much more complicated, so I omit the proof here. So, but anyway, this discussion itself is very important. Not today, but improving some results. Okay, so here is an example. It is called the Hoffman bound. So in this case, we suppose that the graph G is R regular, and let A be the adjacency matrix of G, and let us take the eigenvalues of A in decreasing order. Then the largest eigenvalue is the degree R. Then the independence number is bounded above by this number. So this is the Hoffman's bound. So this bound can be proved using Lovász theta function, the dual version. So this is an idea. In this case, so this matrix Z should be non-negative whenever X and Y are non-adjacent. So it may be a natural idea to take gamma to be of this form. Here, gamma is some scalar. Then this matrix obviously satisfies this condition, okay? So it is natural to take this kind of matrix C. Then, then we have only two variables, Y and gamma. Then it's actually very easy. So if you're interested, then please try to solve it. You can very easily solve it. And this is the result. It's very easy. So you can just try. So that's why we have the Hoffman bound. So this is one proof. Oh, by the way, as I mentioned, alpha of g is bounded above by the theta function, and theta function is equal to its dual, and this y is a feasible solution. And here we take the minimum, so this particular y must be at least theta star of g, because this is a minimization problem, and this is one feasible solution. So this y must be at least this minimal value. So alpha of g is bounded by y. So in this way, Hoffman bound can be proved. There are a few other proofs of the Hoffman bound, but this is my favorite one. Now let us move on to the Delsarte's linear programming bound in 73. So in this case, we take, so this bound can be applied to a specific class of graphs. So here we take a coloring of the complete graph Kn. So edge coloring. So we have D graphs. Okay. So we have D colors of the complete graph. And let us take the adjacency matrix of Gi. So Ai is the adjacency matrix of Gi. Then this coloring is called an association scheme if, so this condition is a bit, not a bit, but algebraic. But Ai-Aj, if we take the product of the adjacency matrices, then there are linear combinations of the adjacency matrix and the identity matrix. So if this condition is met, then this coloring is called an association scheme. So this means that if we take the product of two matrices from here, then it is again a member of this linear span. So in other words, it is an algebra. So this algebra is called the Bose-Messner algebra. So this is a very simple example of an association scheme. So here we have case 6, and this black edge, black color, they form C6, 6 cycle, and the red one, red edges form 2 triangles, and the blue edges form matching. Okay. So I do not give the proof, but this is an association scheme. So as you see here, association schemes are very beautiful objects, very highly regular. And here are some simple facts about the adjacency matrices. So if we take the sum of all of these adjacency matrices, then we get J minus I. This is because this is a coloring, edge coloring. So if we take the sum, then J minus I. So this is just a consequence of, or equivalent condition of this one. And moreover, Ai-Aj is actually equal to Aj-Ai. So they commute. Now, why is that? So Ai-Aj is, by this condition, is a linear combination of these matrices. But all of these matrices are symmetric matrices. So Ai-Aj must also be a symmetric matrix. So Ai-Aj is equal to its transpose, but it is equal to Aj transpose, Ai transpose. But Aj and Ai are symmetric, so it is equal to Aj-Ai. So it is a very simple proof. So Ai-Aj is equal to Aj-Ai. So they commute. So in other words, this Bose-Messner algebra is a commutative algebra. So in this way, we can use the algebraic graph theory very efficiently in this context. And I'm not sure if this is taught in elementary linear algebra course. So in any elementary linear algebra course, you will learn that a real symmetric matrix can be diagonalized. But this is a slightly more advanced linear algebra fact. So if you take mutually commuting symmetric matrices, they can be simultaneously diagonalizable. So this is slightly a bit advanced linear algebra fact, but not very advanced. So if you understand the proof that any real symmetric matrix can be diagonalized, then the proof can be immediately extended to this case. It's not as difficult. So these matrices commute with each other, so they can be simultaneously diagonalizable. So this fact is very important. Now, so because they can be simultaneously diagonalizable, so we can take their common eigenspaces. So we can talk about common eigenvectors and common eigenspaces, etc. So and this is a fact. So you can show that there are exactly d+1 common eigenspaces. So this number should be proved. But anyway, there are common eigenspaces. So as you see here. So as you know, the eigenvalues of the all-ones matrix is n and 0, n with multiplicity 1, and 0 with multiplicity n minus 1. So this eigenspace is actually one-dimensional, spanned by the all-ones vector. And these are the corresponding eigenvalues written in this way. So once you have this kind of table, then we can formulate Delsarte's bound. So in Delsarte's bound, we assume that our graph G is a union of some color classes. So in this case, let us take the first 3 colors. So this is our assumption. In this case, we can apply Delsarte's method. And here again, we take specific Z. In this case, our Z is of this form. So our Z is a linear combination of the adjacency matrices. So let us consider this kind of Z. And let us consider this condition. Then here we can prove the following fact. So this is the dual version of Lovász theta function. It was the minimization problem under this constraint. But here Z is of this form. So the variables are y, this y, and also these coefficients Ti's. So T1, Td. So in this case, there are d+1 real scalar variables. But what is the interpretation of this condition? X and y are non-adjacent. Then the corresponding entry must be non-negative. But our graph is this one. So the first 3 color classes. So non-adjacent means, how shall I put it? The other part. Okay. So these t+1 td, so they must be non-negative. So this condition and this condition are equivalent in this case. Oh, by the way, this matrix does not have diagonal entries. And what about this condition? So, first, let us consider the jth eigenspace. Jth eigenspace. Then now I is the identity matrix, so the eigenvalue is always y. So this is y. And what about j? So as you see here, the eigenvalue of j is n on 0th eigenspace. and all the other eigenvalues are 0. So this is the eigenvalue of J. So when J is 0, the eigenvalue is n. Otherwise, the eigenvalue is 0. Okay. And finally, what about Z? Z's of this form. So as you see here, they can be written as a linear combination. Okay. If we consider the jth eigenspace, then we take this kind of thing. Okay. So this is why we have this kind of sum. So, and the corresponding eigenvalue must be non-negative. So in this way, this problem became a linear programming problem. So we have scalar variable, scale d+1 scalar variables, and we have only inequality constraints. So this is a linear programming problem. Oh, but by the way, because here we take a specific form of Z. So strictly speaking, we have just shown that this is at most this one, because here we are only taking a specific form of Z. So, but actually, you can show that they're equal. So this is a linear program, Delsarte's linear programming problem. Oh, but by the way, this paper was published earlier than Lovász paper. So, but later Shriver noticed that these two bounds are the same in the case of association schemes. So let us consider the case of coding theory. Oh, in this case, the vertex set is this one. Oh, so in the previous slide, n is supposed to be the number of vertices, but in this case, it's not. The number of vertices is 2 to the n, okay? So this is a number of vertices. So this is the table from the previous slide, but this n is supposed to be the number of vertices. So it should be 2 to the n in this case. So it's a bit confusing. So this is the number of vertices. And we define the graph GI in this way according as their Hamming distances. So we color the complete graph according as their Hamming distances in this way, very natural. So in this case, we have n colors. The Hamming distance is obviously at most n. So there are n colors. And this gives a coloring of k 2 to the n. So in this case, we have n colors. So this d should be n in this case. So it's a bit confusing. But actually, this becomes an association scheme. It's called the Hamming scheme. It's a very famous and important example of an association scheme. And we can explicitly find these eigenvalues. These are actually polynomials in J. And as I mentioned in coding theory, we are interested in the independence number of this graph. So the Hamming distance is less than delta. So in this case, we are considering this kind of graph. So the edge set of G is, so we are using the first delta minus 1 colors. Okay. So using Delsarte's linear programming bound, we obtain, in many cases, a very good bound on the independence number of G, or in other words, the maximum size of codes with minimum distance at least delta, as I mentioned before. So this method gives a very strong bound. And using the duality, we can prove many previously known upper bounds, such as Hamming bounds, Plotkin bound, Singleton bound, etc. And by the way, and this is a bit different topic, but so here we are considering association schemes, but a similar thing can be applied to other structures. For example, on spheres. And here I would like to explain one example, the kissing number problem. So this is an interesting problem. So the problem is as follows: how many unit spheres can be attached to a given unit sphere? So in dimension 2, the answer is obvious. So this is a unit sphere, and we can attach 6 spheres, or in this case, circles, right? And obviously, this configuration is unique up to rotation. So this is unique, and the kissing number is 6. It's obvious. And what about dimension 3? In dimension 3, the answer turns out to be 12. Well, by the way, this picture is taken from Wikipedia. And there was a dispute between Newton and Gregory. So Newton insisted that this number should be 12, and Gregory insisted that the number should be 13. But the correct proof was given in rather recently in 1953 and 1956. Actually, Newton was correct. And in this case, there are infinitely many configurations. So these 12 spheres are placed on the regular icosahedron. Icosahedron has 12 vertices. But actually, these blue balls do not touch with each other. So there is a slight space between blue balls. So we can move each blue ball a bit. So that's why we have infinitely many configurations. And in dimension 88 and dimension 24, we know the answers. So in these papers, they use Delsarte's method. So this comes from the E8 root lattice, and this comes from the Leech lattice. And in this case, the configurations are known to be unique. And what about the other dimensions? So the other dimension, we know the answer is 4. In this case, the answer is 24. And this was proved by Musin in 2008. But the preprint was published in maybe 2003. In this case, we use the D4 lattice. And in this paper, Musin used the Delsarte's method. And actually, he modified it. He generalized it. So basically, he added more constraints to prove this kind of result. So his LP bound shows that the kissing number is less than 25. So he showed that the kissing number is less than 25. And we know there is a configuration consisting of 24 points, but the right number should be less than 25. So the answer should be 24. And in this case, as far as I know, we do not know if there are other configurations. So this is one other application. And now let us move on to a different application. So this is one of the most successful applications of Delsarte theory. In this case, we consider the set. So this is a set of k-element subsets of this n set. Okay, all the k-element subsets. So the number of such subsets is n choose k. Okay. And Richard Wilson in 1984 applied Delsarte's method to prove this result. So this is the famous Erdős-Colorado theorem. So suppose that n is at least this number, and we consider a family F such that any two members intersect in at least t points. So in this case, we say that this family is t intersecting. So this is an example of an extremal combinatorics or extremal set theory. So in this case, we are interested in how large F can be. Then this theorem answers this question. So the size of f is upper bounded by n minus t, choose k minus t. And moreover, so if n is greater than this number, and if equality holds, then we have the characterization of optimal families. So like this. So in this case, F should be the K subsets that contain a specific T subset. Okay? So U is a T subset, and we take all the K subsets that contain U. So because every member contains U, so this family is obviously T intersecting. And the size is this one. So this is Wilson theorem, but as I mentioned, this is Erdős-Rado. So actually, Erdős, and Rado show that under the condition that n is sufficiently large. So they prove the theorem under the condition that n is sufficiently large. So the problem is, what do you mean by sufficiently large? And this Wilson's proof provides the exact lower bound on n. So this is his contribution. So actually, if n is less than this number, then there are counterexamples. So this is not the upper bound anymore. There are larger examples when n is less than this number. Oh, I have to hurry a bit. So to prove this linear programming theorem, Wilson used linear programming method. So in this case, maybe it's not so important, but a certain association scheme on the k element subsets. So in this case, it is called the Johnson scheme. So Wilson's result is very strong, but his method it cannot be applied to the case when n is smaller than this number. So as I mentioned, if n is smaller than this number, then there are other examples. But these other examples are all described in this paper, Algebraic theorem. So this is by far the strongest result and complete answer. So they use combinatorial method. So this means that this LP method and STP method are not always the best one. So there can be better methods. So this is the original Erdős-Rado theorem. So, but today, and not today, but we also have the Q analog. So instead of subspace subsets, we can consider subspaces. So FQ is the finite field with Q elements, and omega nkq. In this case, we consider k-dimensional subspaces of this n-dimensional vector space over FQ. So subset K subset is replaced by k-dimensional subspaces. Okay, so this is a natural Q analog, and in this case, we have the complete answer. And the statement is very similar. So in this case, we suppose that the x and y intersect in at least t dimension. So in this case, again, we say it is this family is t intersecting. And we use Delsarte's method to prove the Q analog. So the statement is exactly the Q analog extension to vector space. But I have to be fair. So this is my result. But this bound itself was obtained by Frankel and Wilson in 1986 using Delsarte's method. And also, this case was considered much earlier than Shi in 1975. So this paper uses combinatorial method. So strictly speaking, my contribution is the case when n is equal to twice k. So in my paper, again, I used Delsarte's method. So this is a Q analog. So, and this holds under the condition that n is at least twice k. Then actually, this case gives a complete answer because if n is less than twice k, then we can take the complement, orthogonal complement. So this suffices. This is sufficient. So this is a Q analog. And there, so far, I discussed Delsarte's method, but there are several generalizations and extensions of LP method. So in the case, in coding theory, this is the vertex set, and we used the Bose-Messer algebra. And as I mentioned before, this Bose-Messer algebra is commutative. And this is defined in this way. So the coloring is based on the Hamming distance. So AI, xy entry of AI is 1, if and only if their Hamming distance is I. So this is the definition. So in Delsarte's method, we use pairs of vertices, okay? So we are concerned with pairs of vertices. Then in 2005, Schreiber considered triples instead of pairs. He considered triples of vertices and some group actions to strengthen the LP method. So I do not go into the details, but he used the so-called Terwilliger algebra. So in this case, we consider triples. I do not go into the details. But anyway, so here, this is a zero vector. So this vector is fixed because we use some group action. So in fact, we consider all triples, but by using some group action, one of the vertices is mapped to the zero vector. So in this way, this is one way. And let me show you one interesting example. So suppose that n is a multiple of 4, and let us take the middle graph. So the Hamming distance half n. So this is also called the orthogonality graph. So in some application in quantum information theory, so we are interested in the chromatic and independence numbers of this orthogonality graph. So there are some applications by Galliard. And so this number is a bit complicated, but we have an independent set of this size. So we have a specific construction. And the conjecture is that this is the maximum. So we want to prove this conjecture. Here is the current status. But actually, this is 0, 1. But this problem was considered by Frankel much earlier in 1986. So Frankel considered this case, n is 4 times p to the k, where p is an odd prime. In this case, this is omitted, but this number, okay? So he did not use Delsarte's result, but he used some part of Delsarte's result, Delsarte method, but not exactly LP method. So 4 times a power of an odd prime. So for example, 4 times 3 is 12, and 4 times 5 is 20, and so on. And what about 8? In this case, Delsarte's LP gives the exact number. So this 32 is equal to this case. So this case was done using Delsarte's LP. But Delsarte's LP does not work for n equals 16. When n is 16, Delsarte's method gives 4096. This is a power of 2. But there is a large gap. And this 2304 is this number. But then Declercq and Pasechnik used Schreiber's SDP. Then they showed using computer that this gives this number. So using computer, they show that this is the exact independence number. So this is one successful application of Schreiber's method. But later, Ehringer, Ferdinand, Ehringer, and myself used Frankel's rank argument, modified rank argument, to show that the conjecture is true for all powers of 2. So this is a very short paper, 3 pages. But anyway, this is an interesting application of Schreiber's method. Yeah, I have to hurry. Let me skip this slide. So anyway, Schreiber's method can be used to prove different proof of the kissing number in 4 dimension. So Musin used Delsarte's LP to show that the kissing number in 4 dimension is 24. But we can also use Schreiber's method to prove the same thing. And this is one direction, and here is another direction. So this is the k-element subsets. And previously, we considered the intersecting family, but instead of intersecting families, we can also consider cross-intersecting families. So we take 2 families, F and G, of different size, so K subsets and L subsets. And we impose the condition that every member from F and every member from G intersect non-trivially. So this is called cross-one intersecting. Then we have an upper bound, and we also have the characterization of optimal families. So this is a very natural generalization of the Erdős-Colorado theorem, the cross-intersecting families. Okay. So they used combinatorial method. But later, 10 years ago, Sho Suda and myself used a bipartite version of Lovász theta function band and generalized Matsumoto Tokushige's result to vector spaces. So I did not go into the details, but this bipartite version, this applies to bipartite graphs. And instead of maximizing xj, we maximize this kind of thing. So using this kind of thing, we can prove the Q analog of Matsumoto Tokushige's result. And there are some other subsequent papers by different people. So this is the final part of my talk, but I have to hurry. So I'm already running out of time. So let me just go quickly. So in this case, previously we considered subsets, K subsets. But in this case, we consider all K subsets, not just K subsets. So this is the power set. So let us fix P between 0 and 1. And we define a probability measure on the subset by this formula. So X is a subset of this set. X is a subset. So this measure is P to the size of X, 1 minus P to the N minus the size of X. So this is actually a measure, because if we sum all of these measures, then the number of K subsets is N choose K. So we obtain this formula. But then by the binomial theorem, this is 1 plus 1 minus P to the N, okay? So this is 1. So by binomial theorem. So this is actually a probability measure. And here is the measure version obtained by various authors. So in this case, P is in this range. And again, we suppose that this family is intersecting. Then the measure is at most P. And also we obtain a characterization of the optimal families. Again, the configuration is similar to the previous one. So there is an I such that F is a set of all subsets that contain I. So this is the measure version. And why is it called a measure version? Oh, I'm sorry, maybe my time has already passed. So I will quickly finish. So the reason why it is called a measure version. So we use the binomial theorem, but we can use the law of large numbers. So this is actually a binomial distribution. So it contains, concentrates on the k subsets where n over k over n is roughly p. So this is a binomial distribution where we take p to be 0.3. So this is n is to be 10. What about 40? 100? 400? 1000 and so on. So as you see here, it is concentrating on this part, 0.3. So this is a consequence of the law of large numbers. So in this way, very roughly speaking, this measure version corresponds to k subset version. So this is the final part. I'm sorry. So we have discussed the k subset case. And this is a k-dimensional vector space case. And this is a measure case, subset measure case. Then one thing is left, vector subspace measure version. Okay. So in this case, I should go. I will not go into the details, but there is the Q binomial theorem. So using this Q binomial theorem, we can again define a similar measure, Q analog of the measure, and we can prove the similar result. And so this is what I wanted to say. So this is a recent result with Professor Tokushige. Yeah. And my final message is that this is my recent result, but this range is not best possible. And we have a specific conjecture. So using STP, we can prove this kind of thing, but this is the limit. This is a limit. So in order to go further, we need to have a different idea. Okay, so the last part of my talk was very quick, but I'm sorry, I'd like to finish my presentation here. So thank you very much for your attention.
Okay, thank you, Professor Hajime Tanaka. So please give applause for Professor Hajime Tanaka. So I think the presentation is interesting, but if the audience want to ask questions, so maybe you can ask directly in discussion sessions. But before that, maybe I believe that Professor Eddie has something to show us.
Okay. Okay, thank you, Sadi. So thanks very much to Professor Hajime Tanaka. It's very nice and inspiring talk today. Okay, before we go to the discussion, as usual, we will combine with some song. So this song will be dedicated to Professor Tanaka. Yeah. So this song's actually the title of the song is "Over the Rainbow," "Over the Rainbow," and sung by our colleagues and friends. This is Renovia. With Renovia. Okay, let me present. Yeah, just a moment. Yeah. Okay. Okay. Can you listen the song?
Mm-hmm.
Yeah.
Putus-putus, Pak Edi. Suaranya putus-putus, Pak Edi.
Hah?
Suaranya putus-putus.
Oh,
Mesti diulang nih kayaknya, Pak.
putus ya. Masih putus-putus. Okay, I hope you enjoy. Okay, back to Pak Suhadi.
Okay, so I'm sorry, maybe there's some technical issue because the sound is not
Huh?
hearing.
Okay. Oh,
We
okay.
cannot hear the yeah.
So, Pak Hajime, did you hear the song? No,
Oh, not quite well.
not quite well.
Yeah, yeah.
Shall we repeat it, Pak Joko?
Yeah.
Iya, Pak. I think it's better if you repeat it.
Repeat it. Okay, okay, okay. Oh, just a moment. Why? Kok nggak mau? Padahal udah. Ini tetap aja nih. Sebentar. Okay. Try again. Okay, Pak Joko? No?
Iya. Iya, putus-putus, Pak Edi.
Nggak begitu
Putus-putus ya?
jelas.
Not so
Oke.
clear.
Kayaknya sudah maksimum di sini.
Ah,
Okay, thank you. So I hope now it's better. Now back to Suhadi, Pak Suhadi, please.
Okay. Okay. Now we are ready for discussion session. So everyone who want to ask a question, maybe you can so you can
Raise your hand.
raise your hand, or maybe you can write on the chat room. Oh, please, Professor Akihiro Munemasa.
Hi, okay.
On the
Thank you for a
middle
nice
graph,
talk.
okay.
I have a question on the results on the middle graph where you
Middle
Right.
graph, sure. Yeah, this one.
write the 40 was the small next open case.
Oh, I see. The next slide. Okay.
Yeah, but
Yes.
I don't see the slides on the screen.
Oh, yeah. So as I mentioned,
Yeah, please show me the slides.
Oh, I
Yes,
understand.
yes,
discuss.
you can
I see,
share
I
the
see.
slides.
I have to share the slide. I'm sorry, I forgot to share the slide.
Mhm.
Can you see the slides now?
Yes.
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 Okay. And so this, I said, this is the current status, but actually there's one more. So this is a result with Ferdinand E. Ringer, but a referee of this paper kindly computed the quadruple bound. And this referee settled the case when n is 24. So, so 24 is 4 times 6. So 6 is a smallest composite number. So this is not covered by the previous result. In the previous result, all of them of the form 4 times a power of a prime, right? 4 times the power of a prime. Then this referee settled the case when n is 4 times the smallest composite number. So in this case, the number is this one. And actually, I know who this referee is. So now the smallest open case is 4 times 10. 10 is the second smallest composite number.
So when n is 24, is this number the conjectured one?
Oh, yes. So this, again, in this case, the conjecture is true.
I see. Okay. Thank you very much.
So we expect that the conjecture is always true for every n.
I see. Yeah, thank you very much.
Okay, thank you, Professor Akihiro Munemasa. So, does anyone who want to to ask a question? So, please.
Can I have fun?
Yes, Professor ready?
Okay. So, Pak Hajime, in the beginning, you mentioned that this method is also used to find the Ramsey numbers.
Not this
Could you
method, but
explain little bit about this thing, how to use these methods. Yeah.
so no, this is the different context. So this is not an independent set problem. So their application is very different from ours. So today's talk. So I just wanted to show you different applications of SDP. So in this paper, I do not know anything about it, but they use the so-called flag algebra. Yeah, this paper looks very complicated. So I am interested. It is true that I am interested in this paper, but so far I do not have enough power or endurance to read this paper. So, but maybe I'm sure you are interested in this result.
Yeah, I just downloaded this paper just recently. Minutes, a couple minutes ago, and I saw that this paper, able to refine the upper bound, or sometimes they find the exact numbers of Ramsey numbers for a certain pairs of graph, and mainly for graph with very dense, which are very dense, like complete graph minus some H and others. Yeah, and also there's one of them is also involving the wheels. So that's why I'm interested. To read more probably.
So if we read this paper very carefully, then maybe we can do something.
Okay. Good. Thank you, Pak Hajime. Yeah.
Okay. Any questions again? From Pak Joko, maybe?
Well, no, I just want to say that Hajime has talked about something very wide topic, so it seems that we need some a kind of lecture series to understand your talk.
So today
maybe sometimes in the near future, we can invite you to give a kind of lecture series.
So there were too many slides.
Yes.
Yeah. May I ask just very small questions? When you mention about theta function, Lovász theta functions, can you provide the slide? Can you? Yeah. In the page, I forgot page 2
Not
or
this
3.
one. I'm sorry. This one.
Yes, this. One of the condition of the capital X matrix is the value of entry X, Y is depending on whether the vertices X and Y is adjacent or not.
Adjacent
but
or
the
not.
value itself for both conditions can be equal to 0, right? Because when X is not adjacent with Y, then the value of capital X in the entry XY,
this is 0.
Can be I mean the second one. Greater than or equal to 0. So it means
this is the condition. But it can be 0.
Can be 0. So in both conditions, so it means that in both conditions, whether X and Y is adjacent or not, the value can be 0?
Yeah, it can be 0. Yeah, because for example, let us look at this example. Yeah, this matrix satisfies all of these conditions. Yeah, but for example, let us consider 1, 4 entry. So 1 and 4 are not adjacent. 1 and 4 are not adjacent. And 1, 4 entry is this one. It is 0. So it can be 0.
Oh, okay.
So the condition is that the matrix X is non-negative. So all entry must be non-negative. But it can be positive when X and Y, only when X and Y are non-adjacent.
Okay. Oh, I see.
So it can be 0.
Oh, okay.
Yeah.
Okay. Okay. Thank you. Thank you very much.
Yeah. I see.
Okay, maybe one more question, maybe. Okay, if not, so please give big applause again to Professor Hajime Tanaka, who gave a very nice talk today. So before we close this combinatorial series, so I will give back to Professor Adi.
Okay, so thanks again to Professor Hajime Tanaka for a wonderful and inspiring talk today. And on behalf of the Faculty of Mathematics and Natural Sciences, we would like to present you, Professor Hajime, certificates. We have two kinds of certificates. Please, I will send you by email, but for that I will show you here. Okay.
Oh.
So this is So this is the certificate. So thank you for sharing this valuable knowledge as a keynote speaker on Combinatorics today's series with the title of Linear Semi-Definite Programming Techniques in Combinatorics. And also this is another one. Oh,
another one.
This is another one.
Oh, I see.
So this is I draw it last night. Yeah.
Oh.
I hope you enjoy this.
Oh yeah, I do. Yeah. Thank you very much.
Okay. So thank you very much, Professor Hajime Tanaka. And so that means now it's come to the end of this Combinatorics to the series. And thank you for everybody here to be with us in this series. And see you again next 3 weeks, for the next edition. Okay. Terima kasih, Pak Hajime.
Okay, yeah. Thank you very much for this precious occasion.
Professor,
Okay,
thank you.
very much.
Pak Munemasa and also Pak Banai. Yeah. And Pak Joko, semuanya, Pak Suwadi, and everybody here. Okay. Bye-bye semuanya.
Okay, bye.
Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Okay, see you.
Okay, see you.
Thank you, Hajime.
Oh yeah, thank you very much.
So you should come to Bandung,
Oh yeah.
for giving a series of lectures. Yeah. Okay, thanks a lot.
Yeah, it's very nice to see you. Oh.
Yes. Nice to meet you. Okay, I close this Zoom.
Yes.